Hi, this is Mrs. Basin, and today we're going to talk about factors affecting the reaction rates. So in class, we talked about these a little bit when we did our modeling activity. There are four main things that could affect the reaction rate. One of them is the concentration of reactants. Another one is the temperature of the reactants. You can introduce a catalyst to the reaction, or you can change the surface area of the reactants. So we're going to go through each one of these in a little more detail. So the first one is concentration. So generally speaking, as the concentration of the reactants increases, the reaction rate increases. So what you're seeing here is steel wool burning in air, and then on the right, you're seeing steel wool burn in an environment that has a higher concentration of oxygen. So when steel wool burns, it has to react with the oxygen in the atmosphere. So we know that our atmosphere is not 100% oxygen. So there's some oxygen present, but if we increase that concentration by putting it into a flask that is full of pure oxygen gas, you can see that the burning is much more vigorous in that more highly concentrated oxygen environment. Temperature and rate is another way to change a reaction rate. So again, in general, as temperature increases, the reaction rate increases. So here we're seeing some glow sticks in two different conditions. So the glow stick on the left is in hot water, and you can see that it's glowing a little brighter than the one on the right that's in cold water. That one's a little bit dimmer. You guys probably, as kids, when you went out and came home from trick-or-treating on Halloween with your glow sticks, you put your glow sticks in the freezer. You may not have known why, you just know that it might have made them last a little bit longer. But what you were doing was you were slowing down that glowing reaction rate so that the glowing actually was prolonged and lasted a little bit longer. Another one is a catalyst. So what a catalyst does is it increases the rate of a reaction by decreasing the activation energy of the reaction. Sometimes it also changes the mechanism by which the process occurs. So sometimes it may not only lower the activation energy, it might actually give the molecules an alternate pathway. So instead of something happening in one step, it might split the steps up and have a reaction happen in two steps. And that two-step reaction actually sometimes can be faster than it happening in one step on its own. So you can see the graph here. Look at these energy diagrams like we did the other day, and you can see how that changes. So the green one is the uncatalyzed reaction. That's what this one is here. So you can see what the energy of activation is. For the catalyzed reaction, you can see that that energy of activation is a lot lower. Now notice when you're looking at a catalyzed versus an uncatalyzed reaction, the reactants are in the same place for both reactions, and the products are in the same place for both reactions. The major difference here is the amount of activation energy required. So a catalyst will lower that. Sometimes you'll even see these with multiple bumps on them for the catalyzed reaction, again showing that it's multiple steps. Over here on the right, you see the elephant toothpaste reaction that we do over and over again in here. That's the decomposition of hydrogen peroxide. So normally the decomposition of hydrogen peroxide is very, very slow. Hydrogen peroxide slowly decomposes into oxygen and water. When you add something like potassium iodide to it, that speeds up the reaction. It lowers the activation energy, but it also helps that reaction happen in two steps instead of just one, and that's what makes that reaction happen a lot faster. You can classify catalysts in two different ways. We can call catalysts homogeneous catalysts, which means the catalyst is in the same state as the reactants. So if you have aqueous reactants, the homogeneous catalyst would also be aqueous. A heterogeneous catalyst is in a different state than the reactants. So the reactants might be gaseous, but the catalyst might be a solid, like a surface catalyst that helps those reactants have a place to react. Here are two other examples of catalysts off to the right here. Here's an enzyme catalyzed reaction. An enzyme is a biological catalyst, and it shows the difference between the catalyzed reaction, which would be with the enzyme, and the uncatalyzed reaction, which would be without. Another classic example of a catalyst is a catalytic converter in your car. So what this does is it helps catalyze reactions that lower harmful emissions that would come from your exhaust. So it changes some of those harmful gases into less harmful gases before they leave your car and go out into the atmosphere. All right, finally, we're looking at surface area. So what surface area does is it increases the rate of reaction because you're increasing the amount of contact the molecules have with one another. So this reaction here, what she's doing is she's blowing a powder through a tube. And then you can see as they're lighting it on fire, it has a huge explosion. This is the same kind of thing that happens when you have grain bin explosions, because those particles have so much surface area in contact with one another. A tiny little spark will cause a huge reaction because of that huge surface area involved.